Imagine launching a machine hundreds of kilometers above Earth, and then realizing that once it reaches space, you can't simply send someone up to repair it. Every kilogram matters, every watt of electricity matters, and every drop of fuel can determine how long that satellite survives. For decades, satellites have transformed our civilization. They connect billions of people, monitor our planet, guide aircraft and ships, predict weather, and allow us to explore the deepest regions of space. But satellites are facing a major engineering challenge. How do we make them smaller, smarter, longer-lasting, and more efficient? The answer could completely change the future of space technology. A traditional satellite is essentially a carefully balanced ecosystem. It needs electricity to operate its computers and instruments. It needs communication systems to talk with Earth. It needs thermal systems to survive extreme temperatures. And, depending on its orbit, it may need propulsion to change its trajectory or maintain its position. All of these systems consume resources. That means satellite designers have one simple goal: get more capability from less hardware. And this is where modern satellite technology gets fascinating. One of the biggest improvements is happening in propulsion. Traditional satellites often rely on chemical thrusters, which can provide powerful bursts of thrust but require significant amounts of propellant. Newer spacecraft are increasingly using electric propulsion. Instead of burning large quantities of fuel, electric propulsion accelerates charged particles to generate a small but continuous thrust. The thrust may be tiny compared with a chemical rocket, but in the vacuum of space, it can operate for extremely long periods. That makes electric propulsion incredibly efficient. A satellite can slowly change its orbit while using far less propellant, and that can translate into a much longer operational lifetime. But propulsion isn't the only area being transformed. The real revolution may be happening inside the satellite. Modern spacecraft are becoming increasingly autonomous. Instead of constantly waiting for instructions from mission control, satellites can use onboard computers and artificial intelligence to analyze their own situation. They can monitor their power levels, detect unusual temperatures, identify potential system failures, optimize their orientation, and even determine how to use their limited resources more efficiently. Think of it as giving the satellite a basic ability to manage itself. This is particularly important because communication between Earth and distant spacecraft isn't instantaneous. For a satellite orbiting Earth, the delay is small, but for spacecraft traveling to the Moon, Mars, or beyond, communication can take much longer. The farther we travel into space, the more valuable onboard intelligence becomes. Another major breakthrough is happening with solar power. Satellites depend heavily on sunlight. Solar panels convert that sunlight into electricity, which powers everything from computers to cameras and communication systems. But traditional solar panels have limitations. They take up space, they add mass, and their efficiency can decrease as they age or become exposed to the harsh space environment. Engineers are therefore developing lighter and more efficient solar technologies. Some spacecraft are even experimenting with solar arrays that can unfold into surprisingly large structures after launch. The goal is simple: more electricity without dramatically increasing launch mass. And that matters because getting anything into orbit is expensive. The less a satellite weighs, the easier and cheaper it can be to launch. This brings us to another major trend: small satellites. Instead of building one enormous spacecraft containing every possible instrument, engineers can sometimes deploy fleets of smaller satellites. These spacecraft can work together. One satellite might capture images, another could monitor atmospheric conditions, another could provide communications. Together, they can create a distributed network in orbit. And because individual satellites are smaller, they can potentially be produced faster and deployed in much larger numbers. This approach is already changing how we think about space infrastructure. The future may not be dominated by a few giant spacecraft. It could be filled with thousands of specialized machines working together. But efficiency isn't just about making satellites better at doing their jobs. It's also about making space itself more sustainable. Earth's orbit is becoming increasingly crowded. Thousands of active satellites are already operating around our planet, along with enormous amounts of debris from previous missions. A more efficient satellite of the future may therefore need to think about what happens at the end of its life. Some spacecraft are being designed with better end-of-life strategies. They can be moved into disposal orbits or deliberately guided into Earth's atmosphere, where they burn up. The idea is to make satellites useful throughout their operational lifetime without leaving unnecessary hardware behind. And perhaps the most exciting possibility is that these technologies will eventually work together. Imagine a satellite that uses highly efficient electric propulsion powered by advanced solar cells, managed by autonomous artificial intelligence, and operating as part of a coordinated network of hundreds or thousands of other spacecraft. That isn't just a better satellite, it's an entirely new kind of space infrastructure, a system that can adapt, repair problems automatically, optimize its energy use, change its mission, and potentially operate for years with minimal intervention from Earth. The satellite revolution is therefore not simply about putting better machines into orbit, it's about changing the philosophy of space exploration. Instead of asking, how powerful can we make one spacecraft, engineers are increasingly asking, how much can we accomplish with the least amount of mass, energy, and fuel? And that question could become incredibly important as humanity expands beyond Earth, because the future of space exploration won't be determined only by how powerful our rockets become. It will also depend on how intelligently we use the resources we already have. Smaller spacecraft, smarter computers, more efficient propulsion, better solar technology, and autonomous systems working together. The satellites above us today are already changing civilization, but the satellites of tomorrow could become something much more powerful, an intelligent, interconnected infrastructure surrounding our planet, and eventually, perhaps, reaching far beyond it. This is the next chapter of our civilization in space, and it has already begun.